Hello and welcome to this poster presentation about an electronic device based on impedance flow cytometry, or IFC, that is used to count, characterize, and classify bacteria, microorganisms, and even microplastics from their impedance spectrums. So my name is Karim Bouzid. I am a master's student at Laval University, and I am a student of Professor Benoit Gosselin and Professor Sandro Carrara of the EPFL in Lausanne. So what exactly motivates me to research about this is that very little is known about bacteria. In fact, only about 3% of bacterial phyla are even presently known. We have a bit of information about them because they can be cultured in laboratory, versus the other 97% that when we take them from the field and take them to the laboratories, they die in the way and they cannot be identified or characterized as efficiently. So one of the main motivation is to construct, design a device that can be really simple and really portable, and that can be used for research directly in the field or in situ research. So first of all, the types of microorganisms we want to identify are mostly bacteria, which are in the realm of about 1 micrometer in size. And a bit bigger than that, we have animal cells and plant cells between 10 and maybe 80 micron. And even bigger than that are the microplastics that are about between 1 micron and 1 millimeter. So there's quite the gap in size with them. So what exactly is impedance flow cytometry? It's a technique that can be defined as in this diagram. We have a microchannel here and 2 electrodes on the side in which we send a voltage signal. We're going to measure the current response from the solution. So it's like we measure the conductivity of the solution directly. At first, we measure only the conductivity of the solution. So the impedance should be at a constant nominal value. Afterward, when a particle passes in this microchannel, there will be a spike in impedance, so a variation. And it's that variation in which we are interested, because that's the relative impedance difference caused by the impedance that passes in the microchannel. And by following with the frequency of the excitation signal can give us information, for example, about the cell size or the type of membrane that is used for the cell or microorganism. And at even higher frequencies, we have information about the inside of the particle, like its cytoplasm in the context of cells and bacteria. The main innovation on the technical electronical point of view is that instead of using lock-in amplifiers, like it's typically the case for bulky high-end devices, is that we're going to use a quadrature phase-sensitive detector, which uses a same way of doing, like it's really similar to lock-in amplifiers, but instead of using sine wave, it uses square wave. And that reduces a lot the power consumption of the device, as well as giving performances that are pretty similar. So it's a good way to do a portable device that uses less power. So here we have an overview of the different components of the IFC system. We have a PCB, which with the components form the impedance sensing device. It can sample, for example, it can send a voltage signal at a frequency and an amplitude that is desired, and measures with its ADC the final response of the phase-sensitive detector, so the output current response. So knowing the voltage and knowing the current, we can deduce the magnitude and phase of the impedance. The microfluidic device itself is made of 2 parts, electrodes on PCB and a PDMS microchannel. This PDMS microchannel here is made from a 3D printed mold. So all in all, this whole device is really cost effective. It doesn't cost much, while giving adequate results, as you will see later on. We can see here an overview of the electrodes themselves, which are 200 micron wide, and spaced apart from 250 micron itself. Yeah. We have the microchannel, which has a width of 100 micron. And we can see here the final alignment between the microchannel and the PCB electrodes. The fabrication process is described here, meaning we have the 3D printed mold at first, in which we send liquid PDMS in it. We cure that PDMS at 70 degrees for about an hour to solidify it. And then the PDMS microchannel is replicated on the PDMS following the shape of the mold. Then we bound the PCB electrodes on the microfluidics microfluidic systems using oxygen plasma, so that the whole system is sealed tight and there is no solution leakage. If we look at some of the results obtained from this chip, at first we can do a measurement using only saline water, and we can see that the results we obtain for the magnitude and phase both follow Gaussian distributions. So it's easy to denotate them as being only a mean value and a standard variation. Afterward, we can introduce microbeads, let's say polystyrene microbeads with sizes between 10 and 90 micron, into that saline solution and continue the measurements. We can see at first that when we measure only the solution, then there is a noise that follows a Gaussian distribution at first. And then when a beads passes inside the channel, there is suddenly a big spike in the variation of impedance. And it can follow, and the size of that impedance variations depends on the size of the particle that has passed in the channel. So for example, this one would be probably an 80 micron polystyrene beads, whereas this one would be a much smaller one, maybe 40 micron in size. The really smaller one, for example, 10 micron, cannot be seen because the impedance variations caused by the beads itself is hidden in the noise value of the normal histogram for the nominal value of the saline water. So we can see also that the sensibility of the detection is optimal for beads that are of similar size to the channel width. We've obtained a novel IFC system that favors portability and that can detect accurately polystyrene beads of sizes between 10 and 90 micron. Yes, so I hope you've enjoyed this presentation and you found it interesting, and I hope to see you next time.